Hi everyone. Today we will design a built-up column provided with the Batten system. Similar with the lacing system, here the first 9 steps will be mostly similar with the lacing system. Step number 1, assume FCD value. Assume FCD value. FCD is design compressive stress. Design compressive stress value. We need to assume this value. We can assume this value from 125 megapascal to 175 megapascal. In this range, you can assume the FCD value directly, or you can assume the slenderness ratio value. You can assume the slenderness ratio value in the range of 70 to 100. From this lambda value, you can assume the FCD. You can compute the FCD value from table 9 of IS 800. Table 9 of IS 800. Please be clear. Either you can assume the FCD value directly in the range of 125 to 175 megapascal, or you can compute the FCD value by assuming the lambda value. Step number 2. Compute required cross-sectional area. Required cross-sectional area of the member. Required cross-sectional area is equal to factored load PU by FCD value. We computed in step 1, right? FCD value. The ratio of PU by FCD will give you cross-sectional area required of a section. Now, step number 3. Once you know the required cross-sectional area of the section, you can select the member from IS handbook number 1. Select suitable sections from, please note, here it is not section, it is here we need to select sections from IS handbook number 1. IS handbook number 1. You can select either 2 I sections or 2 channel sections or 4 angle sections. But the area of these sections, suppose if you selected 2 I sections, the cross-sectional area of each section into 2. Okay, the sum of cross-sectional areas of these 2 members should be almost similar or higher than the area required. This is the note you need to observe. Okay, you need to select the suitable section from IS handbook such that the sum of areas of sections should be higher than the required area computed in step number 2. Next, you need to record the properties of the selected members. Record the properties. ఏమేం రికార్డ్ చేయాలి అంటే ఏరియా అండ్ RZ value, RY value, CYY value, okay, and thickness, flange width, all these properties need to be recorded. Once you selected the sections from IS handbook number 1, you need to compute the effective slenderness ratio in step number 4. Step number 4, you need to compute effective slenderness ratio. effective slenderness ratio KL by R effective is equal to 1.05 into KL by R. KL by R. See, this KL value, you can obtain this KL value from end conditions. KL value can be obtained from end conditions. In question, they clearly given, they will be given the end conditions. From these end conditions, you can obtain the effective slenderness, effective length value from table 11. By referring the table 11 of IS 800, you can get this KL value with the help of end conditions. Next, R value. This R minimum value can be obtained from step number 3. Step number 3. From step number 3, you can get this R minimum value. You suppose if you are having RY and RZ value, right? RY and RZ value from IS handbook number 1. From these two values, the lower value will be R minimum. Okay, the lower value will be R minimum. This slenderness ratio, you need to compute FCD value. Compute new FCD value. New FCD value. For this, you need to refer table 9. Table 9. Okay. For this slenderness ratio, effective slenderness ratio value, you need to compute FCD from table 9. Once you know the FCD value, you can compute design compressive strength. Design compressive strength. Design compressive strength or design compressive capacity, PD, is equal to area into this FCD value, new FCD value. Please be clear, this FCD value, we can get this FCD value from step 5. Step 5. This area value you can get from step number 3. Okay. This design compressive stress value, PD, this PD should be greater than PU. PU means factored load. Then it is safe. Okay. If the PD means design compressive strength value greater than PU, then it is safe. Then you can move to the next step. If it is not greater than, then you need to repeat the previous steps. Now I am moving to next step by assuming the PD is greater than PU and it is safe. Now step number 7. Spacing between the sections. Suppose now I have taken the 2 channel sections like this. 2 channel sections. Now the space between these 2 channel sections need to be calculated here. Okay, the space between these 2 channel sections should be such that radius of gyration in y direction should be greater than or equals to radius of gyration in z direction. This is the condition to provide the spacing between 2 sections. Now step number 8, spacing between battens. See, here here spacing between battens, not between the sections. Suppose here I am having one batten and here I am having another batten. Here I am having another batten like this. I have placed this batten with the 3 rivets. Okay, this is one batten, this is another batten. This spacing between these 2 battens can be represented by C. Okay, we need to determine this spacing C in this step number 8. C by Ry should be less than 50, or C by Ry should be less than between 0.7 effective length, 0.7 into effective length. This value we have determined earlier, right? Like this, we need to determine this C value. Step number 9. Forces acting on batten. See, what are the forces coming onto the batten means? First one, transverse shear. Transverse shear is equal to Vt by N. This is the transverse shear. Vt by N. N means number of shear planes. Vt is equal to 2.5% of Pu. 2.5% of Pu means 2.5 by 100 into factor load given in the question. From this you can determine the transverse shear. This is one force acting onto the batten like this. Another force, longitudinal shear. Longitudinal shear can be represented by Vb. Vb is equal to longitudinal shear. Vb is equal to VTC by N into S. VTC by N into S. Okay, better in place of S we will take S dash. VTC by N S dash. Here Vt is a transverse shear. We know 2.5% of Pu. C is the center to center distance between battens. This one. This is the C. Next, N is number of shear planes. S dash is the minimum transverse distance between centroid of rivets. Okay, this distance is known as S dash, where S dash is the minimum transverse distance between the centroids of rivet line. Centroids of the rivet line or rivet group. S dash is the minimum transverse distance between centroid of rivet group, rivet or bolt group. Okay, this distance is known as S dash. Now after longitudinal shear, the third force acting on the batten is bending stress. Okay, this will act on batten like this. Bending stress M, we will denote it with M. Bending stress M is equal to VTC by 2n. VTC by 2n. We know VT value 2.5 percentage of 2.5 percentage of ultimate factored load. C is center to center distance between batten. Center to center distance between batten. N is the number of shear planes. These three are the forces acting on the batten. Okay. Step number 10. Step number 10. Cross section of the batten. Cross section of the batten. See in this figure, suppose I am assuming this is the end batten and this is the intermediate batten. If you consider this one, the distance between end of the rivets and this one, this can be effective depth of end batten. Effective depth of end batten, we can denote it as D dash. Okay, the overall depth means end to end. This is overall depth. This can be denoted by D. Similarly, for intermediate batten, distance between end rivet to end rivet, this is D1 dash. D1 dash. Okay, the overall depth, this one. This is D1. Okay, this is effective depth. This is overall depth of intermediate batten. This is effective depth. This is overall depth of end batten. Effective depth of end batten. Effective depth of end batten is equal to S plus S. Here S is the distance between two sections. This is S. S plus 2 CYY. CYY is the distance of the sections taken from IS handbook number 1. Okay, CYY is the distance of that particular section taken from IS handbook number 1. This value can be get from step number 3, selection of sections. We can get this value from there, and yes, we also calculated this S value earlier. I think at step number 7 or 8, I think. Okay, we also determine the S value. I said S by Ry should be greater than 50, R should be greater than 0.7 into effective depth. Right? I told no. From that place you can determine this S value. Okay, these two values are already we are having. Now step number 10, cross section of batten. Cross section of batten. See, we are dividing the battens into two classes. This is end batten. This is end batten. This is intermediate batten. This is end batten. This is intermediate batten. See, the distance between rivets. This distance is known as effective depth. Effective depth D dash. Now the overall depth of the batten. This one. This is overall depth D dash. D. This is D. This is D dash. Similarly, for intermediate batten, the distance between two rivets is effective depth. Effective depth of intermediate batten can be denoted by D1 dash. Similarly, overall depth of intermediate batten D1. Okay, D1. Okay, these are the effective depths. These are the overall depths. Now, effective depth of end batten. Effective depth of end batten is equal to S plus 2CYY. Here S is the spacing between two sections. We already determined this value from step number 8. I hope you remember. S value should be less than, I said that S by Ry should be less than 50 or 0.7 into effective slenderness ratio. Okay, already we did determine this S value in step number 8 like this. Now CYY. CYY is the distance of that particular section selected from IS handbook number 1. Okay. Next, overall depth. Overall depth D is equal to D dash plus 2 into edge distance. 2 into edge distance. This is the edge distance, right? This is one edge distance. This is one edge distance. D dash plus 2 into edge distance will give you overall depth of end batten. Similarly, effective depth of intermediate batten 3/4 of effective depth of end batten 3/4 into D dash. 3/4 into D dash is this one, S plus 2 CYY. Next, overall depth is equal to D1 dash, and means this value plus 2 into edge distance. 2 into edge distance means D1 dash, this value plus this is one edge distance, this is another edge distance. D1 dash plus 2 into edge distance. Next, thickness. Thickness of the batten is equal to, we can also determine the thickness of batten, that is T value. This T value, this thickness value should be greater than 1/50 into S dash plus 2 into gauge distance. 1/50 into S plus 2 into gauge distance. This gauge distance can be obtained from the properties of that particular section selected from IS handbook number 1. We know this S value already, the spacing between two sections. Okay, like this we can compute the thickness of the batten. Hope you are clear. We have computed the effective depth of both intermediate batten and end batten, and we have also computed the thickness of the battens. Okay, in earlier steps we have computed the forces acting on the batten. If you observe there in that step, we have computed 3 forces which are acting on the batten. First one, transverse shear and longitudinal shear. These are the two types of shear stresses. And the third one is the bending stress. Okay, means here only shear stresses and bending stresses are acting on the batten. Now we need to check the batten is able to resist the shear stress and bending stress. In step number 11, we are going to check the shear stress of the batten. In step number 12, we are going to check bending stress in the batten. How can we check the shear stress? VB by shear force in the batten by area of the batten. Area of the batten is nothing but T into overall depth. T into D. Okay, area is equal to thickness into depth. VB by AB should be less than Fi by root 3 gamma m1. Gamma m1 will be 1.1, right? Fi will be 250. Okay. Next, check for bending stress in batten. 6m by TD square. Already we computed m value. We know D value. We know thickness value. And Fi is 250. Gamma m1 is 1.1. Okay. These are the checks for stresses in the batten. And the last step, connections. We know already we need to determine the strength of the bolt strength of the bolt in bearing and shear. The lower value of this one will be the strength of the bolt. Okay, from this we can determine the number of bolts. Number of bolts is equal to forces acting on that one on the batten by strength of the bolt will give you number of bolts. But be clear, the number of bolts should be greater than 2. At least minimum 2 bolts need to be provided for each batten. Okay, these are the steps involved in the design of built-up column with Batten system. We will discuss an example problem in next video. Thank you.